Hello, hello, and welcome. How's your day going so far? Hope it's going well. This is Power Rule and Substitution, Calculus BC for the AP exam. This is the third class. This time, we're going to go over, as you probably guessed, substitution and the power rule. Up until this point, when we've talked about antiderivatives and integrals, it's been more on a, well, just the area under the curve kind of thing. Kind of conceptual, cerebral, without a lot of the day-to-day calculations required to actually make them work. So today we're going to go over some of the rules that are used to solve a lot of integrals. And again, you can't solve every integral in life, unlike derivatives, where you pretty much can solve every derivative. Integrals is more like a not guess and check, but there are various algorithms you can follow and get pretty much many integrals done, but that's still not all of them. And depending on how you measure the size of the universe of integrals, it can be considered a very small percentage. So if we look back to derivatives, we kind of had a sort of a rule that went something along the lines of, so if you want to take the derivative with respect to x of x to the n, then that gives you x to the n minus 1 times n. And the way that the mnemonic that I kind of used, I guess it's more of a visual mnemonic. I'm not sure if there's a different word for a, sorry, that's supposed to be x to the n. I don't know if there's a different word for visual mnemonics versus audio ones or mental conceptual ones. So I've always thought of it as you take the n, whoop, purple. So you take your n, you move it down here, and since you took it away, it now goes to n minus 1. Because you took away the big N, now you're left with something smaller. And you took it and you move it down. And I like to have as many different ways of knowing things as possible. And I, for some reason, really like visual mnemonics because it kind of creates like a muscle memory feel to it. And if you just do a muscle memory feel, things tend to work a little bit smoother, especially when you're on kind of a time limit. And so that was the mnemonic that I had for finding the derivative of x to the n. Well, now we want to go backwards. And the way that's done, so let's say we have integral x to the n dx, where this is telling you you want to take an integral, which would be considered an indefinite integral because we don't have limits of integration. And since it doesn't have limits of integration, we're basically just going to put a plus c at the end. You'll see after a few examples. So then what I do is take your x to the n, and then I mentally add 1 to it. And then instead of going up the top, this time I go down. So 1 over n plus 1. So the first step is you take your x to the n, you bump it up 1, and then you move it under. So over 1 to the n plus 1. Where for the derivative, my mnemonic did, you took your n, first thing you do is you move it down here, and then you subtract 1 off of it. So the derivative formula is n plus 1 over n plus 1, over n plus 1. So before I get to too many examples of that, in theory, you could take the derivative with respect to x, of the integral of x to the n dx. So this is an antiderivative, plus c. I forgot the plus c. Lots of people forget the plus c always. It's so easy to forget. And I am fairly notorious for abusing constants. And people are like, oh, you shouldn't abuse all those constants. But I'm like, well, they're just constants. Who cares about them? And that doesn't really go over well. You know, constants are numbers too, and they should be respected as such. So try not to forget about the constants. All right, so you have a derivative, or you have a derivative, you have an antiderivative. The derivative of an antiderivative should be nothing, or at least back to where you started. Maybe? Possibly. So we're going to go through this. So this would then be d dx of, I really love these different colors. I abuse this terribly, and I don't mind at all. 0 regerts. N plus 1, make bigger, go down and under, 1 over n plus 1, draw some parentheses. Ooh, we'll do it plus c. Yeah, remembered at that time. Okay, so now we'll take the derivative of this, and we'll have, so first off, we know that the derivative of a constant is 0, so that goes away. And then we'll do n plus 1 minus 1 is x to the n. Oops, sorry, bring it down. I'm getting ahead of myself. So we do n plus 1 here, we took it from up top, so we lose 1, kind of the whole muscle memory mnemonic, but we already have an n plus 1 here. Those then cancel, and we're left with x to the n, as expected. So it seems that this power rule kind of sort of works. Alright? Now we're going to go to a slight tangent, partially to get a little bit of practice. So, in physics, you may have remembered you had kinematic equations. And they told you that if you take a ball and you throw it, the little arc thing that it makes. Oh, maybe if we go this way, get a better camera. Aha, there we go. So idea, have a little person, they throw a ball, and it tells you the arc that things go. And one of the keys to this is you have a constant acceleration. In this case, it's almost always going to be g, gravity. So we're going to start with a slightly simpler example where some guy is standing on a cliff and he has a ball and he drops it straight down. Alright, so we're going to start with the acceleration, which equals a constant. We're just going to call it a. These are actually kind of different. So this is a of t. This is a constant, which is pretty much assumed to be 9.8 meters per second squared. I knew I write them the same, but again, this is mostly a mnemonic. This is actually, every time when I do a kinematic equation, first thing I do is I go through this process of writing out the kinematic equations, because it's easy and quick, and it really keeps you prone from error. So this a of t on this side, that's measured in meters per second squared. When we integrate that with respect to time, what we get is, draw an arrow so I show that it's kind of sort of related but not exactly equivalent. It's kind of my shady way of sliding through life. So we take the integral of velocity, we're going to get, or integral of acceleration, we're going to get velocity with respect to time. And that would be the integral of the other side as well. So we take the integral of both sides. So the integral of a constant, a of t, so this would be equal to a of t to the 0. And we're going to use the power rule on this. So a of t to the 0 then becomes at to the first divided by 1 plus c, which equals at plus c. Now, what does this c equal? Well, in this case, it's going to be the initial velocity. We just dropped this ball, so this initial velocity would be 0. So basically, the idea is if we took the ball and we threw it at the ground, it would have a different speed at any given time period than if we just dropped it. Seem reasonable? So that's where that plus c becomes important with this. And then, since we have meters per second for velocity, we can go one step further. We could probably go many steps further. We are going to go one step further. And we can have distance with respect to time. So again, we'll do the product rule. So we have at plus c, or at plus v naught. So acceleration, which is constant, t, which is to the first, is now going to go to the second, and then bring the 2 around, and we have 1/2 at squared. So now the velocity, initial velocity, is going to act the same way that our acceleration did. So we can view v naught t as v naught times t to the 0 power, which then goes to the 1 power, first power, times t divided by 1, I'm going to leave the 1 off, plus c naught, where this c naught is going to be x naught, the original distance. So you could say how far you traveled, or how far you travel in t seconds. Your position in t seconds depends not only on how far you've traveled, which is this part right here, but also where you started off at, which is the x naught. So every time I get a kinematics equation, the way I always start it off is a equals a, v equals at plus v naught, x equals 1/2 at squared plus v naught t plus x naught. And there's one more kinematic equation that you'll normally see, and what happens is you solve this guy for t, so you do t equals v minus v naught over a, and then you plug that t into here to basically get rid of the t, make it time independent, and you get another equation which is kind of useful. Not necessary, but it kind of makes life oftentimes run smoother. Okay, so that's the general idea of the power rule. One other caveat that's important here is this only works when n does not equal, I think, -1. I think it's -1. Let's try this and see what happens. So x equals -1. I never even mentioned that you can use this with negative values. Yes, you can use the power rule with negative values and fractions. So x to -1, so using the mnemonic, it would go to x to the 0 and then divide by 0. So then you'd get 1 over 0, which can't divide by 0, universe explodes, can't do that. So the integral of 1 over x dx equals natural log of x. I should verify that. Whoop. Integral of 1 over x. Make sure the world doesn't explode. Bam. Natural log. Wolfram Alpha writes log of x, which is fine. Natural log of x. So traditionally thought of as integral of 1 over x equals natural log of x. So you can try the product rule on -1, and if when you go through the calculations the universe explodes because you divided by 0, go back to just slightly before the explosion of the universe and just do natural log of x instead. So one other quick example, if we did x of -2.5 integral dx, we would then get something like x to the -1.5 over -1.5 plus c. So you can use negative numbers and you can use fractions. Okay? Sounds fairly reasonable. And that's pretty much all there is to the product. Oh, one other thing I want to throw in. So we talked about natural log of x. This is going to seem very tangential, and it sort of is. It's one of those Easter eggs. So integral of e to the x dx equals e to the x, which you might have guessed because the derivative of e to the x equals e to the x. So it would kind of feel that it's kind of its own derivative, antiderivative, integral type issue. Right? I know I threw that in quickly, but it's pretty straightforward, and it'll come up a few times for us to review. So it's not the sort of thing where it's going to probably get lost away from you. And that is, let's do cyan power rule. So now on to substitution. I guess is that all the zooming I get for this? Okay. And a little bit more. Okay. 400% zoom. Alright, so now substitution. As you might have guessed, antiderivatives, every single antiderivative is just a way of undoing some sort of derivative that you already have. Yes. So, I guess going back slightly, all the antiderivatives, or all the derivatives, come from limit of h approaches 0 of f of x plus h minus f of x all over x plus h minus x. Plug that in for anything, and you're going to get the rule out for your derivative. Doing a quick one real fast. I guess this is backpedaling. I'm not supposed to backpedal. So for x to the n, if you want to find the derivative of this, you do limit of h approaches 0 of x to the x plus h to the n minus x to the n all over x plus h minus x. X's cancel. And then what you would do is you would expand out the x plus h to the n. And then you're like, wow, what if n's really big? That's kind of complicated. Indeed it is. So you get something like x to the n, h to the 0, plus n, x to the n minus 1, h to the first, plus other things. And eventually you would get n x, that's supposed to be an n, h to the n minus 1 plus h to the n, x to the 0, and then you would subtract off an x to the n, and this would all be over h, limit as h goes to 0. And it's kind of sideways. It's okay. And the way you expand this out, as a quick sidebar, is binomial expansion. So if you have a plus b to the n, you can use Pascal's triangle. This isn't a rigorous proof by any means, but it's a good thing to know in life. 4, 6, 4, 1. So what you do is you just add the two numbers above it. So this would be like 0, so 1's there, 2, 1 plus 1, 2, 1 plus 2 is 3, 3 plus 1 is 4, 3 plus 3 is 6, etc. And you can keep going down. And this is for n equals 0, 1, 2, 3, 4. And what these are the coefficients of the numbers. And so for this one, this would be a to the n, b to the 0, and the exponents will always add up to n. So then you'd have a to the n minus 1, b to the 1, a to the n minus 2, b to the 2, and then the coefficients that go here then would be the first number, so this would be 1, this would be 4, this would be 6, assuming that n equals 4. And if you notice, the way I was able to get this n right here was, for the first section here, it's always just going to count up by n. So 1, 2, 3, and 4. And that's how I was able to get this number, but I wouldn't know the next coefficient. And I knew the second to last one because it does the same thing on the other side of the triangle. Long story short, that cancels, this cancels with one of the h's, you get h to the 0. All the other coefficients have an h in them, which then as the limit goes to 0, it goes to 0, and you are left with nx to the n minus 1. which is your rule for taking power for a derivative. I know I kind of went through that quickly. You're never going to know it. That's just there to build confidence that, oh, when we want to find the rule for an integral, we can just do the limit as h approaches 0 of x plus h minus x all over x plus h minus x. And just the definition of a derivative will kind of give you everything you need for the derivatives. That's not true for integrals. For integrals, I don't know what happened. For integrals, we have to take one of the derivative rules and then basically just reverse it. So substitution, you can find the same rule for that using your definition of a derivative. Nope, I'll keep that. Okay. So now for substitution, our rule for substitution is the inverse of the chain rule. Did I say that substitution is for integrals? Chain rule is the derivatives. And there we go. So the chain rule was f of g of x equals, I'll do it down here, f prime of g of x times g prime of x. And you'll sometimes see this as f little open circle of g. Some people call that the fog of x. But I prefer this notation better, where you have that like the nested. I think it's more obvious. So let's do a quick example of substitution to see how it would work. So, what kind of number should we go for? So this would be a very straightforward. So x squared times 2x dx. We'll say from 0 to 4. So the rule for substitution is, it's not really so much a hard fast rule, but what you want to look for is one thing as a derivative of another thing. So you see here you have x squared. You intuitively, because you're a master of derivatives, at least ideally should be, the derivative of x squared is 2x. And you're like, okay, I see that. So what I'm going to do is I'm going to try substitution. General order of what you want to try in life is, first, if the integral looks like it can be used the power rule, go for the power rule. If the power rule doesn't work, which usually it won't, because they're usually pretty straightforward, and people in life want to give you a challenge, go for substitution. And substitution is looking for one thing that's an integral of another thing. In this, you kind of want to have your spider senses attuned to this. It's going to take practice of a fair number of problems to kind of refine that spider sense. All right, so you say, well, let's say u equals x squared. Reasonable? Reasonable. Now we're going to take the derivative of both sides of this. So derivative of u would be du, and the derivative of x would be 2x dx. You can think of this as the chain rule itself. So x squared is the f, so f of x, that doesn't even really work. X squared, g of x equals x. Derivative of g of x is dx. That's kind of one way to think of it if you'd like. If you still feel a bit uncomfortable with the idea of x squared being the chain rule and getting out dx. If you're comfortable with it, great. So then, from here then, we could just take these numbers and substitute them back into, I'm not going to write 0 there, specifically not writing it. All right, back into our original equation, we have 2x dx, that is du. And then, since I left off these limits of integration, we should probably actually find those. So if we know that u equals x squared, so this up here is x final, this down here is x initial. So for x initial, u equals, let's plug in 0 squared. So this will be u initial, and that equals 0. U final equals x of final x final, which in this case is 4 squared, which is 16. So the limits of integration that we would change would be from 0 to 16 for du. Yes, let's go with that. So then to solve this, we would finish this up using the power rule. So we know it's u to the first. So this would be u squared, because we add 1. Divide, move it down to the bottom. So we have 1/2 u squared. And this represents the limits of integration, 0 to 16. So this would be 1/2. 16 squared, is that 256? I'm pretty sure it's 256. If I was a better computer person, I would know that. So that's what? 2 to the 8th? Is it 2 to the 8th? 16 squared is 256. 2 to the 8 is also, okay, yes, 256. So 256 minus 1/2 0 squared, which is 0. And so we're left with 128 as the final answer. Okay? So I never really learned how to do the whole changing the limits of integration, changing the x initial and x final to u initial and u final. When I went through calculus the first time, I kind of regret it, but the way I got around it is, so you see here, you can see here, so we could have gone, instead of, at this step here, we could have gone off this way. The other way this can be looked at is if we can take u and go back to x. That way we don't ever have to look at the limits of integration for u. Sometimes this saves a step, sometimes it doesn't. So we take u squared, and we know that u equals x squared. So we have x squared squared, and we go from our original limits of integration, 0 to 4. So then we have 1/2 x to the 4th from 0 to 4, which is 1/2 4 to the 4th, which equals 1/2 2 squared to the 4th, which is 1/2 2 to the 8th, which I know from previous forays into Wolfram Alpha is 256 equals 256 over 2, which is back to our original answer of 128. So you see here that we took a different venture here. We bypassed having to find out the limits of integration of u. Basically, we didn't have to convert the 0 and 4, the x initial and x final, to u initial and u final by just going back to x. And by doing that, I was pretty much able to avoid having to learn how to change limits of integration. It's not that hard to change limits of integration, so if you have a chance to know it, I would recommend it. On a slight tangent, you might look at this problem and think, well, wait a sec. We don't have to go through that at all. We could just use the product rule. So you look at, I know, you probably saw this in the beginning. It's not that, yep, you probably saw this and were wondering why I didn't do this from the start. That's just because I wanted to show how substitution works. So here, we could rewrite this as 0 to 4 of 2x cubed dx. And we know we can pull the 2 out. So then we have 0 to 4 of x cubed dx, which then equals 2x to the 4th over 4, which is the same thing we had last time. So we kind of see where this is going. 0 to 4. These cancel out and becomes 2. We then once again get 256, 4th to the 4th. There we go. Over 2, which equals 128. And there's also minus 0 to the 4th over 2, but we know that goes to 0. And so there's three different paths you can take to solve this problem. And all of them are fine. If I saw this problem on a test, I would probably do substitution, just because I have it ingrained in me that if I see one part of a function, which is a derivative of another part of the function, then I just do substitution. But the easiest way is to use the power rule on this one. So that's what we have for substitution and the power rule. So erase these guys real quick. We'll head on down and do some problems. All right. So, green. So the first problem we could come across would be 1 to 4 of t to the negative 3/2. All right. So this has a negative and a fraction, and they use t instead of x, which always kind of throws me off a little bit. So I'm going to start by rewriting this as 1 to 4 of t to the negative 1.5 dt. I like 1.5 because it's easier for me to add and subtract 1 to. So then this would be t to the negative 0.5 divided by negative 0.5. Because you add 1 and then divide by. And I'll do some limits of integration. But I won't actually write them in yet because I don't want to use those CPU cycles yet in my head to solve that. So divided by negative 1/2 is the same as multiplying by negative 2. And the negative on the exponent here is the same as t to the 1/2, which is square rooted, but it's easier for me to visualize at this point as still an exponent. I try to avoid square root symbols when I can. All right, and then solving this, we're gonna get that feels weird. Am I gonna divide by 0? Let's go for this one. All right, so plug in 4. We have negative 2 over 4 to the 1/2, which equals negative 1. Actually, one other thing I'm going to do real quick is with limits of integration, you can reverse them by multiplying them by negative 1. So this is the same as 2 from 1 over t to the 1/2 1 0 to 4. So here then we have 2 over 0 square rooted? That doesn't feel. That's why it's not right, because it's wrong. It's not 0 to 4, it's 1 to 4. Outrageous. Bush League. Well, I'm glad that I caught that and didn't just say, nope, completely impossible, world ends. Alright, so, doing this correctly, so I have 2 times 1 over square root of 1 minus 2 times 1 over square root of 4 which gives us 2 times 1 minus 1/2, which equals 1. 1/2 times 2? Yes, 1. So the answer to this one would be E, 1. So the trick there is it doesn't start at 0, it starts at 1. And then we just do the power rule. And you kind of have to play around with the negatives and switching the exponents with the negative sign. And that's just being cautious. Basic algebra in life, which doesn't mean it's easy, it just means that it should be straightforward and simple. So bench pressing 300 pounds is pretty straightforward. Doesn't mean it's easy. So same idea there. Okay, try the next one. All right, so this one we see x squared and 2x. So first thought is substitution. So we do substitution on this guy. We'll start by saying u equals x squared. U equals x squared. D. I'm going to say u equals negative x squared. Therefore, du equals negative 2x dx. Yes. And then I'm going to rearrange this slightly. So I'm going to say negative 1/2, negative 1 over 2x. Nope, negative 1 over 2. Du equals x dx. So what I have here then is I took this negative 2 and moved it down over here. And so now I have an x and a dx right there. Which I don't like dealing with. I like to make things as simple as possible. So what we have here now is we have the integral of 1 to infinity of u, or e to the u, times, and we have x dx, which we substitute in negative 1/2 du. Oh. I'm going to leave these limits of integration out because they're not, since we substituted in, we'd have to change those from x to u. I'm not going to do that yet, so I'm just going to leave them blank, which equals negative 1/2 integral e to the u. Yep, e to the u du, which equals negative 1/2 e to the u, yep, to some limits of integration, which equals negative 1/2 e to the negative, what did I say u was? Negative x squared. From, and our limits of integration was 1 to infinity, specifically not 0. Bush League, amateurs. So reversing the limits of integration, e to the negative x squared, 1 to infinity, which equals 1/2. Ooh, that one kind of got away from me. 1/2 e to the negative 1 minus e to the negative infinity squared. So this is the same as, a little bit further over, equals 1/2 1 over e minus 1 over e to infinity squared. So e to infinity is already pretty big, and when you put that over 1 and you square the infinity, it gets even bigger, which the 1 over makes it smaller. So you're left with 1 over 2e. So this one should be 1 over 2e. The one that I just happened to accidentally underline slightly earlier. So to go over some of these answers real quick, divergent, you probably don't know what divergent means yet. Divergent just means that the value, the integral, doesn't go to a single answer. So that not single answer could be infinity, which is what they usually mean by divergent, or it can oscillate between 2 or 3 or whatever, how many answers. If it oscillates between answers, then it doesn't go to a specific answer, and therefore that would also be considered divergent. So when the opposite would be saying that this integral converges, and it means that it converges on a single answer. Okay, moving on. Ooh, that looks complicated. All right, using, they even give us u as substitution. We need to convert this over to that. And my goal of trying to get away from the limits of integration failed on this one. It's okay. We will struggle on. So u equals x squared minus 3, which is good because it's kind of in the middle there. Du equals 2x, and then the minus 3 goes away. Dx. I want the x dx kind of alone, so we'll do 1/2 du equals x dx. So then we will rewrite this. I should probably do I assume it's going to be the negative 213, because they're trying to trick you here with leaving the same limits of integration. So I probably could just wing it, but I should probably verify just to make sure in life. If I was doing this for the real test, I probably would just wing it and be like, it's probably negative 2 and 13. So u equals x squared minus 3. So u initial, using negative 1, be negative 1 squared minus 3. Negative 1 squared is 1, positive, minus 3 is negative 2. Check. As expected, u final equals 4 squared minus 3, which is 16 minus 3, which is, I'm going to cheat, 13. Okay, so that's true. Got it. So, moving on with some of these integrals, are they looking for the, sir is looking for the integral. So hopefully this will be straightforward. So we'll go from negative 2 to 13, negative 2, 13, x squared minus 3, so that'd be u to the 5th, times 1/2 du. And we can move the 1/2 to the outside. That's just a property of integrals. We justified it earlier in a previous video by relating it to area under the curve. And if you look at Riemann sums, it makes sense that you can move out a scalar like that. So 1/2 u to the 5th du. 1/2 u to the 5th du. Yep, this one right here. So that one is missing the 1/2. That one has the 2 on the top, and it should be on the bottom. Pretty sure it should be on the bottom. Yep, because when you solve for du, this part right here, that's what gives you the 2 on the bottom instead of the top. And then those just have wrong limits of integration. So that is the introduction to power rule substitution, and we also threw in there exponentials and natural logs. So next time we'll move on to more techniques of integration. Thanks so much.